te doy paso, entonces tú ya das a presentar, ¿vale? So everybody, I think, okay, I think it's in YouTube. So good afternoon to everybody. For me today it's a pleasure to introduce you. Sorry. To introduce you Silvia Viola. Silvia Viola is from Uruguay. She studied in la Universidad de la República. Then she moved to University of Boston for doing her PhD. Then after a couple of postdocs in Berlin and Erlangen, she is now group leader in the Max Planck for the science of light in Erlangen. So thank you very much, Silvia, for accepting the invitation to give us a seminar today, and please.
Thank you very much. So I will share my screen. Let's see. Okay, so you see my screen? Yes.
Yes.
Very good. So yeah, thank you very much for the invitation. I think so. I've given by now a few Zoom seminars and talks, but I think this is the first one that is being streamed live on YouTube. So there is always a first time for everything. So thank you for giving me the opportunity. I will be talking about a topic which we have been working in my group for a couple of years now, which is cavity optomagnonics. This is a field that deals with the coupling of photons and magnons, and at the level of the single quanta. And I will tell you a little bit about the status of the field and also of our efforts, theoretical efforts, to basically push the boundaries to enter into the quantum regime of these systems, or to explore the quantum regime of these systems. Okay. No, this is not working, so maybe. Okay. I am just a second. My okay. Now I'm not sure what is going on, but now it seems to work in a weird way, so I can go over with my slides. So as David was saying, we are a research group located at the Max Planck for the Science of Light in Erlangen in Germany. So this is our building. We don't get to enjoy it so much these days. So our meetings, group meetings, look a little bit more like this. So we are a theory group, and we are interested in the physics of hybrid quantum systems. So what do I mean when I talk about hybrid quantum systems? So here I kind of collected a very non-exhaustive list of systems which enter the category of systems which we are interested on. So for example, optomechanical systems, electromechanical systems, where either photons or electrons can couple to mechanical vibrations. This is just an example. And the underlying characteristic of all these systems is that they are at a scale that is a nanoscale, microscale. So they are systems that are large enough such that one can design them. One is interested in designing their collective excitations, for example, how they can vibrate, and at the same time, how different degrees of freedom can couple, so to design their coupling. And on the other hand, these are systems which are small enough that quantum effects can be relevant. And we are interested in understanding these quantum effects and also harnessing these quantum effects. So if we think about what these systems are good for, one can think in terms of applications in quantum technologies to process, communicate, or store quantum information. But these systems are also interesting from a fundamental perspective, for example, to understand how macroscopic can a quantum state be, in the spirit, for example, here of the well-known Gedanken experiment from Schrödinger's cat, in which say a cat is put in contact with a true quantum system, so to form a ultimate hybrid system. And this leads to the absurd case of the cat being alive and dead at the same time. So what I will be talking today is actually specific to hybrid quantum systems, which are based on magnetic elements. This is quite a new field. It has it's evolved in the last 6 years or so. But although it's a very young field, as you can see in these figures, it's become very popular, and there's a plethora of systems that are being investigated nowadays. For example, magnetic systems interacting with microwave radiation, using this interaction to couple them to superconducting qubits, on-chip realizations of these systems, coupling to optical photons, or coupling to other degrees of freedom, more predominantly vibrational degrees of freedom, so phonons. So since we are going to be talking a lot about magnons, let's just level the field just to say what a magnon is to start with. So a magnon is the elementary magnetic excitation of a magnetically ordered system. So it's the quanta of a spin wave. So if you think it's the analogous of what phonons are to mechanical vibrations, but in this case, we don't have a motion of the atoms. What we have is that the spins in the ordered magnetic material can precess around their equilibrium position in some ordered, in some coordinated way, and this forms a spin wave. So what is a magnon? A little bit more intuitively, if you want. So I can think of, if I have a magnetically ordered system, I spin it, I can flip one spin, but this flipping of one spin is happening non-locally. So this is shared by all the magnetic material. So it's a collective excitation which involves a macroscopic number of spins. So if I look at a semi-classical picture of this, so what I would see, and what is the easiest mode to look at, is what we call the homogeneous or Kittel mode, in which all spins are precessing in phase. So as you see in this small video. So this is just one example of one magnon mode. So this is the semi-classical or the classical picture of what a magnon mode would be. So why do we like them? So actually magnons inherit the very rich physics of the magnetic materials. So they are quite interesting excitations. They are robust and they are tunable. So we will see that one can tune, for example, their frequency by also, for example, applying an external magnetic field. They are excitations that they consume, or they are low power excitations in the sense that they don't present ohmic losses because there is no charge transport associated with them, or not necessarily. And they are amenable to miniaturization, so we can pack them in very small volumes. And in this talk, we will be interested in coupling magnons mostly to photons. As a rule, this coupling is quite small, but we have a trick. So one can think in terms of using a cavity, so a box for the electromagnetic radiation. And this cavity, one of the effects that it has is that it will enhance the spin-photon interaction. Not only that, it introduces new physics in the system. So this is one can explore concepts of cavity quantum electrodynamics in magnetic systems. And in particular, also it will introduce, for example, back action in the system. And magnetic systems, on the other hand, are very particular, or like something very unique about these systems is that one can explore also non-trivial ground states of these magnetic systems. So for example, the presence of magnetic textures, so spins which are ordered in a non-trivial, non-homogeneous way. So this makes these magnetic systems also quite interesting from this point of view and quite unique. So this is the outline of what will be coming in the next half an hour or so. So I decided to split what I'll be talking about in two regimes. One is coupling magnons to photons in the microwave regime, and the other one is coupling magnons to photons in the optical regime. And there I will give just kind of a flavor of what we do in our group. That's a few examples of our recent work. So we go ahead to the microwave regime, and just to give you a little bit of perspective. So this is a little bit how the field started. So approximately 6 years ago, it was demonstrated experimentally the strong coupling regime of magnons coupling to microwaves. And what you see here is the setup that was used. So one of the possible setups that can be used. So this, what you have here is it's a microwave cavity, a copper microwave cavity, and in one of the corners there is a small sphere of YIG, which is yttrium iron garnet. This is a magnetic, very magnetically ordered material, which is transparent in the infrared and also presents a very low dissipation for the magnon excitation. So in this magnetic sphere, one can probe different magnetic modes. And as I said before, the easiest mode to probe is the Kittel mode, or the homogeneous magnetic mode. So this is what I represented here. For you to have an idea, I told you that the frequency of the mode can be controlled by an external magnetic field. So roughly 30 milliteslas or tens of milliteslas will give you a frequency of this mode in the range of gigahertz. So what they use here is this tunability to actually tune the frequency of this magnetic mode in resonance with one of the microwave modes inside of the electromagnetic field inside of the cavity. And you see here that there is here, where the modes should cross, there is actually an avoided crossing, so there is a hybridization of the modes, and this indicates the strong coupling regime. So how, sorry, sometimes my arrows work and sometimes they don't. So this coupling is strong, and one of the reasons this is strong is because we are in the regime of resonant coupling. So how does the magnetic mode couples, or the magnetic system couple to the electromagnetic radiation in the cavity? So you see it here, it's simply a dipolar coupling in which the magnetization couples directly to the magnetic field part of the electromagnetic radiation. So basically, when you are here, you can exchange one photon with one magnon, and so you have quasi-particle polaritons that are formed, which are part magnon and part phonon. So the field has evolved since then, and I think one of the publications that stirred a lot of excitement in this field is this one here. So they, in the group of Nakamura in Tokyo, they showed that they can use the same setup, but they can, in the other corner of the cavity, they can put a superconducting qubit and demonstrate a coherent coupling between the magnon excitations to the superconducting qubit via the microwave cavity. And more recently, they have shown that they can use the setup to basically build a single magnon detector via measurements of the superconducting qubit. So this points towards basically doing quantum optics with, but with magnons instead of with photons. So what we proposed is that, and this is a work that we put out very recently, is that these systems can be used actually to generate macroscopic non-classical states of the magnetization, and in particular spin cut states as I showed before, this kind of Schrödinger cat that I showed in the introduction. So our proposal is based on the concept of heralding. That means that one entangles 2 degrees of freedom, in this case, the magnons and the photons, and by measuring one part of the system, one can herald or create or collapse the other system in a desired state. So here one would measure the photons and put the magnetic or magnon system in some desired state. So what we need, or what our proposal needs, is basically the same kind of setup that I showed you before, a microwave cavity and a magnet. But in this case, what we need is an anisotropic magnet. So what you see here is an ellipsoid. And this is important because the magnetization fields in this, due to anisotropy in this magnet, will lead to a Hamiltonian of the system, which is this S now is the creation annihilation operators of the magnons. So if I would have an isotropic or isotropic magnet, I would just have basically a harmonic oscillator, but the anisotropy term will lead to terms that look like this. So they are squared in these magnon operators. So this is basically a squeezing term. And one can evaluate the quantum ground state of the system and look at the fluctuations. And what one sees is that just these are concepts that come from quantum optics. So the ground state of the systems is what is called squeezed. So one sees that the fluctuations on top of this quantum ground state are anisotropic, as you see in this figure. So now this is the part of the magnet. Now we want to couple it to a microwave field in a cavity. The microwave coupling comes, as I said before, by just via that dipolar coupling. So you obtain a Hamiltonian that looks like the one we had before, but on top of it, we have the cavity photons, which are these A. So the A operators create and annihilate photons, and we have the interaction between the cavity and the magnet. Now we can do the same process of calculating the ground state of the system, the quantum ground state of the system. And what we will see is that the ground state of the system actually is an entangled state of photons and a few flipped spins, which is a little bit counterintuitive, but this is what one finds. And now we take this system, and what we propose is by doing, now we created the entangled state, so to say, and then what we propose is by measuring the state of the microwave cavity, one can herald a spin cut state of the magnetization of the magnetic system, which is what is indicated here. So this measurement can be a single photon measurement that probably experimentally is more challenging, but it can also be a parity measurement of the cavity, which is less restrictive. So you see that now the state that one finds, basically you have 2 blobs, and what this indicates is that basically these are 2 semi-classical states of the magnetization, in which in a superposition in which the magnetization is pointing simultaneously in 2 directions. We also evaluated the experimental limitations, and we find, as usual, nature doesn't really want you to see big non-classical states. But what we show is that for cryogenic temperatures less than 5 millikelvins, there are the conditions given for generating relatively large squeezed magnetic cats. So we think that this, or we show that this is in principle, it's challenging, but in principle possible with state-of-the-art experimental state-of-the-art. So before moving to the optical regime, let me just go briefly over another proposal that we have done in the microwave regime. And this one incorporates also the mechanical degrees of freedom of this system. So we propose that these systems can be used as a primary thermometer that can work in the cryogenic regime. So for this, as I said, we use another degree of freedom in the system, which are the phonons. The coupling between the magnetic degree of freedom, the magnons and the phonons, has also been demonstrated, and well, this is known, but also at the single quantum regime. This is one example in which they use the same kind of setup to probe the microwave cavity setup to probe the coupling between the magnetics and the vibrations. So this coupling is just an example of classical is an example of magnetoelasticity. And in this kind of setups, because you've seen again this kind of sphere of this yttrium iron garnet material, for the sizes of the spheres that they were probing here, it turns out that you can calculate the phonons modes are in the kilohertz regime, and the magnons keep being in the gigahertz regime. So one cannot couple them resonantly. One has what is called a parametric coupling, and this is what is shown here. So you see now B are the phonon operators, create annihilate phonons, and the M, before what they were S, but now they are M. So the M's create and annihilate magnons. And you see here I have a process in which I have two magnon operators coupled to single phonon operators. This is an example of this parametric interaction that I was talking about. It's needed to compensate for this mismatch between the frequency. So now the system couples the phonons to the magnons via the magnetoelastic interaction that I showed you before. And the magnons can couple resonantly, as I also showed before, to the microwaves. And the idea is that the thermal vibrations, so this is immersed in some bath at a temperature T. And the idea is that this temperature T will be, so the phonons will have thermal vibrations at this temperature T, and they will be imprinted on the magnetization of the magnetic system. And one can use the microwave cavity to measure, by measuring some noise, some intelligently chosen noise correlations, to actually measure the temperature of the system. So this is, and this is what we showed, which is one can construct a thermometric relation between a particular combination of two quadratures of the noise of the microwave cavity. This is what one measures. And you see that this relation depends on T, but it doesn't depend on any internal parameters or any parameters of the system. So this is what is called a primary thermometer. It doesn't need calibration. It's just a thermometric relation that does not need to be calibrated, and also it works at very low temperatures, which is actually quite difficult. So the fact that it can work at low temperatures is partially because one is using microwaves to probe the system that produce less heating than optical photons. This is quite compatible with current experimental setups. The only thing is that one has, so there are some certain experimental imperfections that can be quite detrimental for this thermometric relation. So this is also, we also studied this kind of limitations, but in principle is quite promising setup also with doable with the state of the art in these systems. So now we turn the page, we go to the optical regime. So we want to look at the coupling of magnons to photons in the optical regime. And just as a motivation, why would we be interested in doing this? So one motivation can be if we would be able to couple this magnetic system so good or as good to light as we are able to couple them to microwave radiation, then we could use these magnons as a transducer, quantum transducer between the gigahertz regime where information is processed to the optical regime where information is yes.
Yeah. So before you move to the next section, there are questions in the chat about how do you estimate the couplings, both this coupling to the cavity, so between magnons and the cavity photons,
yes.
and between the magnons and the phonons. So
yes.
How do you estimate them? How do you calculate it?
So okay, let me see if I can my computer is behaving weirdly, but let me see. So here, for example, for the phonons, one can go to the, I don't have the expression here, but one can actually derive the expression of the magnetoelastic energy in the system. And one sees basically that the magnetization couples to different components of the strain tensor in the system. And depending on which processes one is looking at, for example, this coefficient here, one will be proportional or will be the integral of the overlap between certain components of the strain tensor times the magnetic mode. If I go to here, to the microwaves, so here it's even easier to see. So this magnetization I will be able to write as a sum of, so I can, it will have a certain mode function for certain modes. In this case, for the homogeneous mode is just homogeneous, so it doesn't have any structure. But then that means that there will be some overlap of the magnetization with the field. In this case, usually the field, the magnetic field is taken to be basically constant over all the structure. So that means that here you basically will be, you will have a coupling which is dictated by the volume of the sample, and you can show that actually if you do a Hodgson-Primakov transformation of these spins, you will get an enhancement of the coupling by a factor of square root of the number of spins participating in the in the mode. But I think this will be, this is, I just cannot show with writing, but I think this will be clearer when we go. I will show it explicitly how one does it in the optical regime. So I think this will be.
Sorry for, but in this figure, I can see that you have a coupling of 0.1 gigahertz or something like this, right?
Yes, it's quite large. Yes,
it's quite large.
Yes, yes, I think it's in the hundreds of megahertz, if I remember correctly. So the cooperativities in this system can reach 10 to the 3, so it can reach thousands. And what you want to do to get a good coupling is basically to have a good match between the two modes, and you want to have cavity mode volume, which is very small. So these are the two things that will boost your coupling. But this will be clear. I do have explicit expressions for the optical regime, so maybe we can move further.
But we have another question, sorry. Yes. Carlos asked how the coherence is understood in a magnon excitation.
So if you, so the magnetization dynamics is governed by what is called the Landau-Lifshitz-Gilbert equation of motion. And there is, and that means that you basically, the magnetization will, if you put, just think that you have a magnetization and you put it in a, just think in terms of a homogeneous magnetization or a spin, and you put it in a magnetic field, it will start to precess. And but this precession, if you don't have any, it will just keep processing, but there will be dissipation processes which tend to damp this precession. And this is encapsulated in this Gilbert damping term. And this is something which is known classically in magnetism. And this is measured for a lot of materials. It turns out that yttrium iron garnet has a very low Gilbert damping. And this Gilbert damping will give you the line width of the excitations. So in here, the line width of the magnon mode is around 1 megahertz. If I remember, yes, it's 1 megahertz. So it's also basically it's similar to any other dissipative process, but in this case, it's just that the dynamics, the equations of motion are a little bit different, and the dissipation, what it does is not to change this the size, so to say, of the magnetization, but it just damps its precession. I'm sorry, I don't have the. I just realized I don't have the equation here to show. Is that more or less clear?
I think, yeah.
Okay. But yes, so basically, and just as without thinking too much, if you have a magnon mode and you will measure it, you will see that it has certain line width, and this line width will have a contribution for this from this Gilbert damping. If you go to very high or very large excitations, then you start getting other processes such as magnon-magnon interactions that can broaden your mode even more beyond this Gilbert damping. Okay. So let me see. Yes, so I was here. So now we are going to the optics, to the optical regime. And so how does the coupling to optics work? So this is a little bit different than what I showed in the microwave regime, because now we have photons that have 200 terahertz frequencies, and we want to couple them to magnon excitations, which are gigahertz excitations. So I don't have the possibility of coupling them resonantly. So, but we know that magnetism and optics coupled to each other. This is what we all know as the Faraday effect. So, and it's just when one has linearly polarized light that is going through magnetized material, its plane of polarization will rotate in an amount which is proportional to the Faraday constant of the material, which actually for YIG is quite large, and well, the length on which the light traveled in the material. So one can understand this Faraday rotation if one looks at the permittivity, and one sees that the permittivity of the material, if it is magnetized, acquires a complex or imaginary antisymmetric term, which reflects that that the time reversal symmetry is broken in the system. So it's this term that you see here. If you now go to the light propagating in the material, and you use this permittivity, you will see that this is good exercise. You will see that at the end of the material, you will have this basically that the polarization is rotated. So there is basically the light which is circularly, the right circular polarized and left circular polarized are seeing slightly different refraction coefficients. So it's kind of a circular birefringence induced by the magnetization. At the microscopic level, one can show that this is due to spin-orbit coupling in the material, but at this, we are staying with this more phenomenological approach, if you want, because this is all we need for calculating the coupling. So what we see is that if now we take this permittivity and we into the electromagnetic energy of the system, the electromagnetic energy of the system will acquire a correction, which is what you see here. This is the time averaged electromagnetic energy of the system. And you see that it couples the magnetization density in your material to what is called the optical spin density. So this is the electric field part of the electromagnetic radiation which is propagating here. And you see that it's, so this cross product, so this vector is pointing perpendicular to the plane of polarization of the light. So you see two differences with what I showed you before with the coupling of microwaves. One, and now we have a magnetization which is coupling to the electric field part of the electromagnetic radiation, not to the magnetic field part. And it couples basically to the intensity, right? So we have two electric fields here. So it's quadratic in the electric field. So that means that if I quantize this interaction, I would get now a spin operator corresponding to the magnetization, but I will need two photon operators. So again, a creation and annihilation operator for the electric fields. And so this is again an example of this parametric coupling that I showed you before. So the coupling, so the coupling was this coherent coupling between optical photons and magnons was demonstrated simultaneously, actually, by 3 groups in 2016, almost simultaneously. And the setup is what you see here. Now the magnetic material, the sphere that you see here, is not in a microwave cavity, but so the cavity is formed by the material itself. By total internal reflection, it can confine optical modes inside of it. So this is an example of a whispering gallery mode. And so they can probe the coupling by coupling externally an optical fiber to these modes. And the coupling will be, the coupling between the magnons and the photons is weak, but is, as I said, can be enhanced by the cavity. In here you see that since the photons are basically trapped for a while in the cavity, what the cavity intuitively what it's doing is just extending the length, the effective length of that the light goes through, and therefore the coupling. This is kind of an intuitive way of seeing it. Now, the coupling is enhanced, but still its value is quite small for applications. We have shown, however, that its theoretical limit is much larger and is comparable to the values that you can find in optomechanical systems, which have been quite successful. And what we showed also is that what one needs to reach these couplings is a better overlap of the modes. So if you see here, we have an optical mode, which is basically close to the surface of the sphere, whereas the magnetic mode lives in it's a bulk mode. And the other issue is that these fields, you see the size is 500 microns. So actually these cavities are too large. So you would like to go to the diffraction limits of sizes in the micrometer region. So this is leads me to another example of why these magnetic materials are important and is interesting, and is that the regime, the micro scale is quite interesting for magnetic systems, but because a competition of the interactions in the system, so exchange interaction and dipolar interactions, create what I showed you before, so textured magnetic states, ground states, and the paradigmatic example is a vortex in a cylindrical structure. So these vortices have been demonstrated in very diverse cylindrical structures, including in YIG. And what we thought, okay, how can we use this to our advantage, these magnetic textures? And also, first of all, how will the photons couple to magnon excitations on these systems? And now I get to the coupling, and this is how what I was saying, that I will show one explicit form of how one can get the coupling. So now I rewrote slightly differently the coupling of what I showed you before, the magnetization coupling to this optical spin density. And what we can do now is we want to go beyond this kind of homogeneous magnetic mode, and tractable, the way that one can do some analytical progress is to work in what is called the spin wave limit. So we consider small oscillations of the magnetization on top of a ground state, which can have a spatial dimension variation. So if we do this, now we can basically quantize this, excitation on top of the ground state. And formally, this what one does is a Hodgson-Primakov transformation of the spins, of the local spins. But at the end of the day, what one can write is that this excitation will be a sum over the magnon modes, which are represented by gamma. These are the magnon mode functions. These are the creation annihilation operators for the magnons. And this is very similar to what one does with the electromagnetic field. So now we have the electrical field mode functions in the cavity, and the A's are the creation annihilation operators of the photons. So you see now a specific example of how one can calculate these couplings. So now if I put everything together, I get a Hamiltonian which scatters magnons with two photons, between two photon modes. So if you want, this is kind of a Brillouin, cavity-enhanced Brillouin scattering, and all the information of the modes is in this coupling here. And the coupling will be given by the overlap of the magnon mode functions with the photon mode functions. And actually, this is the difficult part to calculate. And this is what we have developed a method to calculate this. And the issue is that, as I said, magnetic systems can be quite complex. And as a rule, except in very simple cases, one has to calculate this magnon mode functions numerically given a geometry. So this is what we did for the case of the magnetic vortex. So now we considered a cavity, which is this magnetic dielectric, which hosts a magnetic vortex and can also host whispering gallery modes. And the coupling between the two can be calculated by, on one side, calculating using micromagnetic simulations, which actually simulate what I was telling you before, the Landau-Lifshitz-Gilbert equation of motion for each spin in the material subject to the field of the other spins, and the optical modes, and then we just need to put them together and calculate this coupling. So I see I'm now, how much time do I have? We started a little bit late, so but I have maybe a couple of minutes, right?
Yeah, and 5 if you want.
Okay, so I will just now show you an example. So the issue is how to calculate this, and as I said, this requires a lot of work. So this is what we did, for example, for the case of the magnetic disk that I showed you before. So what you see here is an example of if you also apply to the system a magnetic field. So you see this is the vortex in the magnetic material. This is the magnetic texture. So this is how a vortex, the cross-section of the vortex looks. And then you have to look at the modes, the magnetic modes of the system on top of this texture. So this is what you see here in these blobs. This means basically we are looking at modes that is like this vortex here is kind of, it basically is vibrating like a string. And these are different flexural modes. And then we can use our method to calculate the coupling for each different mode, which you see here. So in this case, for this particular example, we showed that the coupling can be actually tuned by an external magnetic field, and we predicted values of the cooperativity of 10 to the minus 2. So actually, the cooperativity gives you an idea of how strong that coupling is to the dissipation channels in the system. For, say, quantum protocols, one would like the cooperativity to be larger than 1. So 10 to the minus 2 is yet not in what we would like. And of course, this is also a theoretical value. So in experiment, we will be probably even lower. But even with these relatively low values of cooperativity, one can think in terms of protocols, and we showed that one can, again, by using heralding, a heralding protocol, one can produce this time non-classical states in the form of magnon Fock states by measuring. So this is an all-optical protocol, and is generated by measuring. The state is heralded by measuring the optical photons. So I will be very brief here. So we are going, so what these systems show us is that so the design of the systems is promising to obtain larger couplings. And this is a little bit, it's important because if one wants to do any progress with optical photons, one needs to improve this coupling. So we took inspiration in the field of optomechanics, where one designs a system to colocalize modes. And in this case, so you see a periodic array of holes with a defect in the middle that can colocalize an optical mode and a magnetic mode. So we now we have to basically repeat the procedure, but now we have a kind of a crystal, and we have to calculate the modes and the bad structure both for the optical modes and for the magnetic modes. So this is what we have done. So as you see here, the band diagram for the optics, this is kind of very common to do in optical systems. And the new thing here is that we propose to do this in structures which are also magnetic, so magnetic dielectrics, and you can also host magnon modes. And then by looking at the symmetries of the modes, one can choose the appropriate modes to reach good coupling. So this is these are very recent results. We hope to put them online in the next couple of weeks. So we showed that okay, this is possible. There are also quite relatively large values of the couplings can be obtained. But nevertheless, these kind of, we also learned a little bit how to optimize the geometry of the systems. But nevertheless, this for the optics is not so good because these structures are very lossy from the optical side. So at the end of the day, the cooperativities, which is kind of this figure of merit, is still low for these design systems. But as I said, this shows promise in the design, in aiming for designing the systems. So I hope that I convince you that the systems are interesting. The state of the art in the microwave regime, so it's ripe for generation. So for starting to use the system for generation of macroscopic non-classical states, and for example, for to harness this coupling at the single quantum level for applications, for example, a thermometer working at cryogenic temperatures. The optical regime, so there's still a lot of work that needs to be done in terms of designing the system for improved coupling values. And we have we are working on this and developed a method that allows us to work with basically arbitrary magnetic textures. What I didn't have time to show you is that these systems are very interesting also to explore in other directions, new systems and new physics. And for example, we have also worked with, and we have worked and we are also doing currently work on cavity optomagnonics, or interaction of light with antiferromagnetic materials. But okay, this will be a whole different talk. So just advertise it here. And just the outlook is, if we look at the collection of quantum hybrid systems, this is basically what was missing in this picture of, well, basically everything coupling to everything. And I leave you with, I would like to leave you with a message if you want. So this is the cover of a book, Michael Faraday, his Christmas lectures. And as you see, he was interested on the various forces of natures and their relations to each other. And well, 150 years after, we are still interested in this topic, but we just need to put a quantum. So we're interested in this topic, this interactions, various forces of nature at the quantum level. Thank you very much.
So thanks a lot, Silvia. We cannot clap because at least consider clapping virtually. So we have several questions, okay?
Yes.
So Carlos, the guy asked before, insist a little bit and say, and in the case of pure dephasing, where dissipation does not occur, this was the question about dissipation. I mean, I think you explained dissipation, classical. So if you use Landau-Lipschitz, it seems classical, right? So the question is, if there is no dissipation, what happens? Okay, I don't know. I'm trying to interpret the question. But...
well, there is. I don't know. I have to think about it. First of all, there is always going to be dissipation. So there is always going to be so what one sees in these magnetic systems is if you go to very low temperatures, basically there is a dip in the dissipation goes down, 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 and there is a dip, and then it goes up a little bit. And that means, so at different temperatures, different dissipation processes are predominant. And at very low temperatures, it's believed, because of this kind of, it saturates the dissipation, and it's believed that this is due to two-level systems. At the level of, this is, from like the magnetics, if you want the new thing that one could think in terms of the magnetics is how these dissipation processes happen and this Gilbert damping. Now, once I worked in the spin wave limit of small oscillations of the spin around their equilibrium position, and I quantize the system and I work with magnons, then I can apply all concepts that I can take from basically single particle or like the usual methods, but I'm not sure what exactly is he meaning with dephasing. But what one has to be also careful with magnetic systems is that what I said with this, so treating the system with magnons, etc., it's valid for in this spin wave limit. So if one starts driving the system a little bit more strongly, there will be deviations of this, and it will induce magnon-magnon interactions, and these magnon-magnon interactions will contribute to the decay of these modes into other modes. And these systems, so for this, so the coherence length or this can be up to hundreds of microns. Maybe this is where the question is coming from or going to. So the coherence length, so the coherent can be preserved up to hundreds of microns.
Okay. So there are more questions. So people ask regarding coupling between vortex and photons in gallery modes. Does this coupling only affect to flexure modes, also to the most trivial gyrotropic mode? So
yes, so actually this I didn't show, but actually when you have a very thin magnetic film, which is patterned in terms of a disk, then the vortex will look more like the vortex that you would expect, not what I showed. And then we calculated actually the coupling to this gyrotropic mode. And actually this is the first thing that we did, because in this case, analytically, and one can benchmark our numerical simulations. So yes, yes, the only problem is that in this, so you need to engineer your system such that you can also have an optical cavity. Yeah. So what we did is to think in a heterostructure in which you have a magnetic film sandwiched by silicon nitride disks, such that you can form an optical cavity. And in that case, you can calculate a coupling between the gyrotropic mode and the whispering gallery modes. What I showed is actually basically these flexural modes. It's basically a bit of a generalization of this gyrotropic mode. So these are the modes which are localized at the vortex core.
Okay, more questions. How does one single magnon excitation looks like in the case of a vortex?
Depends on it depends on the mode that you're looking at. So for example, for the gyrotropic mode, so basically it's always a deviation of, or like a local flipping of the spin, which is distributed over the whole sample, but the question is how it is distributed, right? And for example, for what was mentioned before, this gyrotropic mode, what this mode is that you see that you have a magnetic vortex, which is a static ground state configuration. And now say that you basically, you kick this vortex a little bit out of its equilibrium position, then the center of the core of the vortex will start rotating around its equilibrium position. So basically this is this gyrotropic magnon mode, and you see that the magnetic texture basically is that as the vortex core is moving, it will this means just that the magnetic texture is moving, so to say. And this is, yeah, I'm not sure if I can give a better picture than that.
Yeah. So there's another one. Regarding cut states, does this effect depend on the orientation of the magnet with respect to the magnetic field created by the cavity? I mean, I think that, I don't know, you have like, if you have anisotropy, you have an axis, right?
Yes.
And this is...
So what is important is, that's a good question, I don't remember. So what is important is the direction of the static magnetic field with respect to the anisotropy axis. You see that basically they are competing. For the actual microwave field, we just, I think this is not, so it will just change the details of this coupling here, but not more than that. So basically the static configuration is the important one. And then in practice, so here we consider that one mode is one mode of the microwave cavity is coupled. What I didn't mention is that actually this protocol works in the dispersive regime. So actually it's the system doesn't have to be in resonance. And that means so that the microwave mode and the magnon modes, they are shifted in frequency. And that means that actually there can be a coupling to several, in reality, there will be a coupling to several, probably several microwave modes will be relevant with different configurations of the field. But basically, this is just incorporated, or this is, so if you remember, this G basically is basically given by this integral, right? So then it will just, the direction of the magnetic field with respect to the magnetization will enter through this cross product. So it will just change the actual value of the coupling, but it will not have any other effect.
Thanks. So I have just a last question.
Yes.
Not to make this too long. So it's respect the last part of your talk, when you make this kind of crystal. So if I understand well, you are kind of coupling a localized excitation, which is the magnetic mode, with an optical mode, which is like a propagating mode, an extended mode, right? It's right or not?
No. So the idea is that this structure, so that it forms a Bragg mirror both for the optics and for the magnetics.
Okay. So you are creating also a cavity for the optical mode.
Yes. Yes. So and you see it. So so you see this is like the continuum of the band. Basically, this is a defect which is in the band gap of the crystal, and the same is we try to do the same for the magnetics. So this in optics, this is basically people do this all the time with but with basically with silicon. Yes, with the dielectric that they use to make these structures is silicon, and so for this to work, the idea is that okay, you need a magnetic dielectric like YIG, so that can basically form a cavity for both. So
in your simulations, you use this YIG material, and you are doing these MUMAX simulations to simulate the profiles of the modes that are here.
Yes. So and yeah, and then one has to think in what are the symmetries of the modes, and one would the magnetics is quite complex because I mean it's good because that means that it gives you a lot of knobs to turn. For example, if you apply an external magnetic field, this will also determine how your modes look like. So you can choose to apply it in the direction of the crystal, perpendicular to the crystal, in this direction, or perpendicular to the slide, and all of these details will dictate the symmetries of your magnetic modes, and which are the ones that you want to match to the symmetries of the optical spin density to improve the coupling. Yeah.
And just the last question. I mean, if we think just this setup you are doing as a cavity for the photons, you said that the quality factor is not so good. Or...
Yes. So the thing is, so we started very optimistically and very ambitiously with optical with photonic crystal structures, which we know are good photonic cavities or better, and that means that instead of having an abrupt defect here, so this you see here, basically it's just one hole is missing, more or less. I mean, one has to also control what is this distance, but basically we took a hole out, and this creates a defect in this crystal. Now, what people have, and I can show you this, what people have perfectioned is how to do this in a better way, so that basically now you have what is happening here for the optics is that you have an effective index of refraction here given by the system with the holes, an effective refraction index here, which is basically the one of the material. And here you have an abrupt change between these two indices. So there's an impedance match between the two, and this is not good for losses. So you want to avoid that. And what people do is this kind of structures in which the defect is basically tapered. So this is better. So there is no abrupt impedance mismatch, and this is has better quality factors for the optics. The problem is that when we started to understand the magnetics of such kind of structure, basically it was very difficult. So we just went back 2 steps back, if you want, and said, okay, to understand what is happening with the magnetics, we need to treat a much simpler structure. And this is why we settled with this, just to understand how to do these kind of things for magnetics. And this, you see in this kind of optimization, what we saw is that now if you use this kind of elliptical holes, it kind of goes in the direction of this tapering. So this is better for the coupling, but still not for the losses. And now one has to think how one can modify this, such as that one can also get the optical losses into control without losing the nice magnon modes. Yeah.
Okay. So yeah, I think it's time. So thank you very much again for the nice talk. So there are some people already in the chat saying that it was a nice talk.